The synthesis of molecular knots has been a challenge for chemists due to their complicated topology. However, the potential applications for their unique properties have kept this area of study active. I will be defining what a molecular knot is and explaining that they can be found in naturally occurring biological molecules, the nomenclature used for knots, the different synthetic approaches, and conclude with the future of molecular knots. Molecular knots are classified as mechanically interlocked molecules, and they are systems with non-self-intersecting loops that cannot be untangled without breaking a covalent bond. This is not to be confused with other species within the same class, such as catenanes, systems made up of interlocking rings which do not contain chemical bonds between them, and rotaxanes, systems which contain two components which are held together through intermolecular interactions or physical barriers to dethreading instead of a chemical bond. Synthetic molecular knots are a challenging concept to grasp. However, these structures can be found in well-known biological systems such as DNA, RNA, and proteins. The formation of knotted structures in DNA is catalyzed by the ATP-dependent topoisomerase enzymes, which here you can see topoisomerase 4, which also aids in the unknotting process of DNA. Knots found in proteins are classified as open knots, since the backbone does not form a closed curve, which is a key feature of knots. The exact evolutionary advantages of naturally occurring knots like these are currently unknown, and many scientists believe that these unique structures play a key role in the functionality of biological systems. We can classify the different knotted structures through observing the types of crossings and the number of crossings in a molecule, and this is now commonly annotated using the Alexander-Briggs notation, as seen here, where the X component informs us on the number of crossings that are in the knot, while the Y subscript is the order of the knot, which has been classified as seen in the Rolfsen knot table. For example, the trefoil knot with 3 crossings would be annotated with a 3 and a 1, while there are 2 different pentafoil knots with 5 crossings, annotated with a 5 and a 1 or a 5 and a 2. Since the beginning of the research into interlocked molecules, many efficient methods of preparing and characterizing molecular knots have been proposed, so that these complex and aesthetically beautiful molecules with knotted topologies can be understood, and their potential can be utilized. Despite macrocyclization being a kinetically unfavorable process, the synthesis of molecular knots is possible due to the increase in entropy when polymetric structures form closed rings with a reduced number of components. Common approaches for mechanically interlocked molecules include random assembly and covalent template-directed synthesis. However, knots have been made using the more efficient supramolecular template-directed synthetic strategies like non-transition metal templates, passive transition metal template, and active transition metal templates. The synthetic routes I will be discussing today will be using passive or active transition metal templates, as coordinating molecules around transition metal centers provide a guiding force, resulting in an efficient way to interlace and interlock molecules for knotted structures. In the passive transition metal template approach, the transition metal is used to bring the building blocks closer together, as well as efficiently orientating them through metal-ligand coordination, which increases the chances of a reaction occurring in the correct sites from ligands in the same coordination sphere. However, in the active transition metal template approach, a synthetic strategy developed by Paul McGonigal, the transition metal is used as a template as well as the catalyst for the formation of the covalent bond between the building blocks, resulting in a faster one-step synthesis for which only a stoichiometric amount of the transition metal is required, which is not only highly efficient, but is also allows for elucidation of the reaction mechanism. There are 2 common routes to the synthesis of molecular knots. One forms helicate intermediates. For example, a linear helicate is formed in the synthesis of the first synthetic trefoil knot by Jean-Pierre Sauvin. A circular helicate is formed in the synthesis of the pentafoil knot by Jean-Francois Aime and the 8-crossing knot by Jonathan Danon. And the other forms a woven grid intermediate, like the 3x3 grid from the synthesis of the endless knot by David Lee. This is followed by the connection of the ligand strands through reactions such as immination or alkene metathesis. To gain a better understanding of the synthetic route behind molecular knots, we first need to look at how the trefoil knot, first synthesized by Jean-Pierre Sauvin, was done using the passive metal template approach, later employed by various chemists. Firstly, it was crucial that the complexation between the two copper plus cations and the two subunits result in the formation of a highly stable double helix structure B2. This is dependent on the choice of subunits, and here a 1,10-phenanthroline compound connected via their two positions with a phenyl group at either end is used for the synthesis. Secondly, the formation of the double helix structure needs to be favored over any other possible complex from the combinations of the starting material used. The double helix were then connected through a reaction with an ether halide to form the trefoil knot and demethylated for the copper 1+ cations to be removed. Although the crystal structure here may not look like the traditional trefoil knot, a conformational change using the Redemeester move can be used to transform from a D2 symmetry to the typically seen D3 symmetry. Here are some more examples for the synthesis of different knots. The subunits coordinate with the transition metal center, which positions them in a manner that allows reaction to occur between atoms within the same coordination sphere, creating a covalent bond between them. The trimeric knot found here forms via a circle double helicate around the zinc 2+ centers. The endless knot employs a strategy for the synthesis of knotted molecules where a woven grid is created around a transition metal cation template, which could be a zinc 2+ or iron 2+ in this case. This method is relatively novel because weaving causes strain on the supramolecular compound, since the distances between the transition metal cation and the ligand strands might increase, weakening the coordination interaction. However, this synthesis is possible due to a range of different factors which are brought about from the careful considerations of the choice of subunits utilized for the initial gridded structure, all the cations and anions which the knotted compound coordinates around, and the conditions in which the synthesis takes place. The braiding of 3 of these subunits form a circular triple helicate around the iron 2+ center to bring the 8-crossing knot. All subunits contain a terminal alkene group so that ring-closing metathesis catalyzed by Hoveda-Grubb's second-generation catalyst can occur, and the complex can be demethylated to form the knots. In conclusion, the unique properties of molecular knots are brought about as a result of the presence of mechanical bonds and restricted conformation, which can be exploited by scientists in various disciplines. 2 examples of the application of molecular knots are found in catalysis and materials. This pentafoil knot can initiate and regulate a reaction because it promotes the formation of carbocation through the cleavage of carbon-halogen bonds through the trapping of halides in this center cavity. Halide anion abstractions can also result in the generation of catalytic species, which could be achieved using this catalyst as well. The 2-step synthesis of endless knots from woven grid intermediates, as talked about before, presents an approach for the synthesis of 2-dimensional woven fabric. Through connecting the ends of the coordinated subunits belonging to the intermediate of the woven 3x3 grid, the formation of 2-dimensional interwoven fabric can be achieved. Thank you for listening to my presentation.